Late 1945. The air over Kasumigaura smells of burnt metal and desperation. At Japan's premier naval flight school, a damaged American fighter sits surrounded by engineers, their faces drawn with exhaustion. The bent-wing aircraft looks almost alien against the backdrop of shattered hangars and skeletal trees. Its inverted gull wings stretch outward like the arms of a fallen angel, and beneath the crumpled cowling rests something that would shatter every assumption Japanese engineers had made about American industrial capability. This isn't just another captured enemy aircraft. It's the F4U Corsair, powered by the Pratt & Whitney R2800 double Wasp engine, a mechanical monster producing 2,000 horsepower from 18 cylinders of American engineering. Within days, Japan's finest technical minds would gather around this machine, disassemble it bolt by bolt, and confront a truth more devastating than any bomb. They weren't just losing the war on the battlefield. They had already lost it in the factory. The Corsair had been force-landed somewhere near the flight school, its pilot likely killed or captured. Japanese salvage teams found it relatively intact, missing only propeller blades, and suffering damage to one wing where fabric patches covered torn metal. The discovery sent ripples through Japan's naval air technical arsenal at Yokosuka. Captain Tanaka Yoshio, chief of the engine analysis section, received orders to transport the wreckage immediately. By dawn, the aircraft was already being loaded onto flatbed trucks, its wings folded as designed, a feature that would later fascinate Japanese engineers who struggled with carrier operations. The convoy moved slowly through roads, cratered by American bombs, past factories reduced to skeletal frames, past civilians who no longer looked up at the sound of engines overhead. When the Corsair arrived at Yokosuka on a grey morning in early 1945, technicians circled it in, silence. They had examined captured American aircraft before, Grumman Hellcats, whose rugged construction had surprised them, consolidated Liberators, whose sheer size had seemed wasteful. But the Corsair was different. Even damaged, it radiated a sense of brutal efficiency. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Tanaka approached the engine, cowling slowly, running his hand along the aluminum skin. The Corsair's nose was long, absurdly so, giving the pilot almost no forward visibility during landing approaches. American pilots called it the Ensign Eliminator for its tendency to kill inexperienced aviators. Yet the US Navy had built over 12,000 of them. That number alone defied logic. Japan's most advanced fighter, the Nakajima Ki-84, had achieved fewer than 400 units in production, despite being desperately needed. How could America afford to build thousands of an aircraft so difficult to fly that it killed its own pilots? The answer, Tanaka suspected, lay hidden beneath the cowling. He ordered his team to begin. The first panel came off easily, held by quick-release fasteners that any mechanic could operate without tools. Japanese aircraft required specialized equipment and hours of work to access their engines. This one opened like a door, and when the cowling fell away, revealing the massive radial engine beneath, every man present stopped breathing. The Pratt & Whitney R2800 double Wasp sat before them like a mechanical god. 18 cylinders arranged in 2 rows, each cylinder larger than a man's fist, connected to a crankshaft of staggering complexity. The entire assembly gleamed with precision machining, every surface smooth, every bolt torqued to perfection. Engineer Sato Kenji, who had spent 5 years designing engines for Nakajima, knelt before it as if in prayer. "Impossible," he whispered. "This cannot produce 2,000 horsepower." But it did. Intelligence reports confirmed it. The Corsair could reach over 400 miles per hour in level flight, faster than any Japanese fighter except experimental prototypes that rarely worked. It could climb to 30,000 feet, carry 2,000 pounds of bombs, and still outfight the vaunted Mitsubishi Zero in every category except low-speed maneuverability. All of this from a single engine designed in 1937. Tanaka ordered a complete disassembly. Every component would be measured, weighed, and analyzed. They would understand how America had achieved this, even if it took months they no longer had. The work began that afternoon. Technicians removed the engine mounts, careful not to damage anything. The reduction gearbox came off first, revealing a 2-to-1 planetary system that drove the massive 13-foot propeller. Japanese engineers crowded close, examining the gears with magnifying glasses. The tolerances were microscopic. Metal touched metal with such precision that no gasket was needed. Oil couldn't leak through gaps that didn't exist. "How do they machine this?" Sato asked aloud. No one answered because no one knew. Next came the supercharger, a 2-stage mechanical system that compressed intake air to maintain power at high altitude. Japan's Nakajima Homare engine had attempted something similar, but manufacturing problems had crippled its reliability. Pilots complained of power loss above 20,000 feet, engines that overheated, cylinder heads that cracked. The Homare was designed to produce 1,900 horsepower. In practice, field reports showed it barely reached 1,300. The R-2800 produced 2,000 horsepower, reliably, day after day, mission after mission. Some Corsairs had flown over 200 combat sorties without engine failure. The supercharger casing was a single forged piece, not welded sections like Japanese designs. This eliminated weak points, reduced weight, and improved heat dissipation. But forging something this large required hydraulic presses that Japan didn't possess. Even if they had the blueprints, they couldn't manufacture it. Sato's hands trembled as he measured the impeller blades. Each was machined from solid aluminum, not cast. The surface finish was like glass. He knew immediately that Japan's industrial tooling couldn't replicate this. Not at scale, not quickly, perhaps not at all. The crankshaft extraction took an entire day. 6 men struggled with the weight as it emerged from the crankcase, a massive forged steel shaft with counterweights positioned with mathematical precision. Tanaka ran his hand along its length, feeling for imperfections. There were none. Not a scratch, not a tool mark, not a single flaw in the heat treatment. "This is a work of art," he said quietly, "but they make them by the thousands." Fire. Technical excellence wasn't Japan's problem. They had brilliant designers, capable factories, skilled craftsmen. The Homare engine was conceptually sound, even advanced, but America didn't need brilliance. They needed production. And production required something Japan had never achieved, the marriage of engineering and industry at massive scale. The R-2800's development had cost Pratt and Whitney 4 years of testing, from January 1938 through October 1942, just to perfect the crankshaft. 4 years to solve vibration problems that would have destroyed lesser engines. They had tested counterweights, changed metallurgy, and ultimately designed second-order counterweights rotating at twice crankshaft speed to cancel energy surges from firing pistons. This level of dedicated research was a luxury Japan couldn't afford. By the 3rd day, the cylinder heads were removed. Sato lifted one carefully, turning it in the light. The cooling fins were incredible. Not cast with the head, but individually forged and precision machined before being attached. Each fin was thinner than paper at the edges, maximizing surface area for heat dissipation. The R-2800 generated enormous power, which meant enormous heat. These fins were the secret to keeping 18 cylinders cool while running at maximum output for hours. Japan's engines used cast fins, thick and heavy, unable to dissipate heat efficiently. The result was chronic overheating, especially in tropical climates where Japanese forces fought. Mechanics in the field reported engine failures within 30 hours of operation. The R-2800 could run for 1,500 hours between major overhauls. The difference wasn't design philosophy, it was manufacturing capability. Forging thin, cooling fins required advanced metallurgy and precision equipment. Japan had neither in sufficient quantity. Even their best factories struggled to maintain quality control as material shortages worsened, and skilled workers were drafted into combat units. Tanaka compiled his findings in a report that grew longer each day. The R-2800 weighed 2,480 pounds. Japan's Mitsubishi Kasei engine, producing only 1,850 horsepower at best, weighed over 1,700 pounds. The Americans had somehow created an engine 40% more powerful while adding less weight proportionally. The fuel system used direct injection in later models, eliminating carburetor problems that plagued Japanese designs at high altitude and during negative G maneuvers. The electrical system was standardized, every connector identical, every wire color-coded. Any mechanic could troubleshoot it in minutes. Japanese aircraft electrical systems were bespoke nightmares, each plane slightly different, requiring experienced technicians and detailed schematics. But the most damning discovery came when they examined the engine's construction documentation. Stamped into various components were manufacturer codes: Pratt & Whitney, Ford Motor Company, Buick, Nash Kelvinator. The R-2800 wasn't built by a single factory. It was assembled from components manufactured by multiple companies across America, each making identical parts to microscopic tolerances. Ford had built engines. Ford, the automobile manufacturer, they had converted car factories to produce aircraft engines overnight. And not just any engines, but the most complex, powerful engines in the world. By the time production ended in 1960, over 125,000 R-2800 engines had been manufactured. Japan's entire aircraft industry produced 9,089 Homer engines during the entire war. For every Homer, America built nearly 14 R-2800 seconds, and the R-2800 worked. As Captain Tanaka sat in his office late one evening, surrounded by disassembled engine components and technical drawings, he understood why Admiral Yamamoto had warned them. "I fear all we have done is awaken a sleeping giant," Yamamoto had said after Pearl Harbor. The giant hadn't just awakened, it had industrialized warfare itself, transforming raw material into military power at a rate that defied imagination. Japan had the knowledge. They had the designs, copied, analyzed, and understood. But knowledge wasn't enough. The real weapon wasn't the Corsair or its engine. The real weapon was the system that produced them. Factories that ran 24 hours without stopping, supply chains that never broke, workers by the millions, including women and teenagers, building identical parts with microscopic precision. Quality control that turned every mechanic into an interchangeable specialist. The report Tanaka submitted to Naval High Command in March 1945 contained over 200 pages of technical analysis. Every measurement, every material specification, every design choice was documented in meticulous detail. His conclusion was brief, devastating, and irrefutable. The American R-2800 engine represents the pinnacle of mass production engineering. While Japanese factories can produce engines of comparable design sophistication, we cannot match the manufacturing precision, material quality, or production volume required to field such engines at scale. The gap is not technical, it is industrial. The report circulated through Tokyo's war offices in complete silence. No one disputed its findings. No one proposed solutions. There were none. By April 1945, American B-29 bombers were reducing Japanese cities to ash. The aircraft production network that had briefly made Japan a manufacturing power was collapsing. The small workshops and family-run suppliers that produced components for Mitsubishi and Nakajima were burning. The skilled workers who could handcraft intricate parts were dying in firebombing raids or being conscripted as soldiers for the final defense. Meanwhile, in America, production was still accelerating. Pratt & Whitney had gone from 5,000 engines per year before the war to 50,000 per year by its end. The R-2800 powered not just the Corsair, but the Republic P-47 Thunderbolt, the Grumman F-6F Hellcat, the Northrop P-61 Black Widow, and numerous bombers and transport aircraft. It was everywhere, reliable, powerful, unstoppable. Japanese pilots who survived encounters with Corsairs spoke of them with a mixture of respect and dread. The Japanese had nicknamed it Whistling Death for the distinctive sound its engine cooling vents made during high-speed dives. That whistle meant death was coming, fast and inevitable, from a machine that could outrun, outclimb, and outfight anything Japan could field. By the war's end, Corsairs had achieved an 11-to-1 kill ratio against Japanese aircraft. For every Corsair lost in air combat, 11 Japanese planes were destroyed. The final entry in Tanaka's personal journal, dated August 14, 1945, one day before Japan's surrender, contained just 3 sentences. "We decoded their engineering. We could not decode their industry. This is why we lost." The captured Corsair remained at Yokosuka until American occupation forces arrived in September. They found it partially disassembled, its engine in pieces, surrounded by Japanese technical documents and drawings. US intelligence officers photographed everything, fascinated by the thoroughness of the analysis. The Japanese had understood the R-2800 perfectly. They simply couldn't build it. Years later, when a German engineer from Blohm and Voss examined a recovered R-2800 and saw that the 2 crankcase halves were machined with such precision they required no gasket and didn't leak oil, he reportedly said, "If this is what the Americans can mass produce, then the war was already lost." He was right. The war had been lost not in the skies over Midway or the jungles of Guadalcanal, but in the factories of Detroit, the forges of Pennsylvania, and the assembly lines where American workers, many of them women, turned raw steel into engines of impossible power. But the story of the Corsair's impossible engine begins years earlier, in 1936, when Pratt and Whitney engineers gathered in a Hartford, Connecticut conference room to discuss a problem that would define the next decade of aviation. The US Navy wanted fighters that could fly farther, faster, and hit harder than anything currently in service. That meant power. More power than any single engine had ever produced. The challenge wasn't just generating horsepower, it was doing so reliably, at high altitude, in extreme conditions, and in an engine light enough for a single-seat fighter. The R-1830 twin Wasp, Pratt & Whitney's most successful radial, produced around 1,200 horsepower, excellent for the time, but insufficient for the Navy's ambitions. They needed something revolutionary. Chief Engineer George Meade proposed an 18-cylinder design, 2 rows of 9 cylinders arranged radially. This would be America's first 18-cylinder aircraft engine. The only other 18-cylinder radial in existence was the French Gnome-Rhone 18 litres, which produced 1,300 horsepower from 56 litres of displacement. Meade's team aimed for 2,000 horsepower from just 46 litres. This meant each cylinder would need to produce extraordinary power, which meant extraordinary heat. Heat was the enemy. Generate too much, and cylinder heads cracked. Cooling fins melted, pistons seized, engines exploded. The team spent months on the cooling system alone. Traditional cast cooling fins wouldn't work. The cylinders were too small, too closely spaced, and generated too much thermal energy. The solution was radical. Each cooling fin would be individually forged from aluminum, machined to paper-thin edges, then attached to the cylinder head. This maximized surface area while minimizing weight. It was expensive, difficult, and required manufacturing techniques that barely existed. But it worked. When the first R-2800 prototype ran in May 1939, it produced 2,000 horsepower exactly as designed. The sound must have been glorious. 18 cylinders firing in perfect sequence, the crankshaft spinning without vibration, oil pressure steady, temperatures within limits. For the first time in aviation history, 1 horsepower per cubic inch had been achieved in a production-ready design. But reaching 2,000 horsepower was only the beginning. The real challenge was keeping it there, hour after hour, without failure. And that's where the crankshaft nearly destroyed the entire program. The crankshaft is the heart of any engine, converting the linear motion of pistons into rotational power. In a massive radial like the R-2800, the forces involved were staggering. 18 pistons firing in rapid succession, each generating thousands of pounds of force, all transmitted through a single steel shaft. The shaft had to be perfectly balanced, or vibrations would tear the engine apart. The initial crankshaft design looked perfect on paper. Pratt and Whitney's best metallurgists had specified the alloys. Master machinists had crafted the forgings. But when installed in test engines, something went wrong. The vibrations were brutal, hammering through the engine at specific RPM ranges. Bearings failed within hours. Connecting rods cracked. One test engine literally shook itself off the test stand, breaking mounting bolts and crashing to the floor in a shower of sparks and oil. The problem was harmonic resonance. The firing sequence of 18 cylinders created complex vibration patterns that reinforced at certain frequencies. Traditional counterweights couldn't cancel them all. For nearly 4 years, from January 1938 through October 1942, Pratt and Whitney's engineers fought the crankshaft. They tested different metals. They adjusted counterweight positions. They changed firing orders. Nothing completely solved the problem. Finally, a breakthrough. Engineer Leonard Hobbs proposed second-order counterweights, small masses that rotated at twice the crankshaft speed, specifically designed to cancel the troublesome vibrations. It was elegant, complex, and required additional gearing that added weight and complexity, but it worked. With the new counterweights installed, test engines ran for hundreds of hours without failure. Vibrations dropped to negligible levels. Bearings lasted. The R2800 was finally ready for production. By the time the Corsair first flew in May 1940, with an R2800 humming in its nose, the engine had been tested more thoroughly than any power plant in history. Pratt and Whitney engineers had run durability tests, high-altitude tests, extreme temperature tests, and endurance tests that lasted for days. They had pushed prototypes until they failed, studied the prototypes, failures, redesigned the weak points, and tested again. This obsessive perfectionism created an engine that pilots would come to trust absolutely. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. In Japan, engine development followed a different path. Not worse, not inferior, but constrained by resources and industrial capacity that would prove catastrophic. The Nakajima Homare, Japan's attempt to match engines like the R2800, was designed with brilliance and built with desperation. Development began in 1940, around the same time Pratt and Whitney was solving its crankshaft problems. Nakajima's chief engineer, Nakajima Chikuhei, envisioned an 18-cylinder radial that would be compact, powerful, and relatively lightweight. The design was impressive. At 118 centimeters in diameter, it was barely larger than the 14-cylinder Sakai engine that powered the Zero. Yet it promised 1,900 horsepower, nearly double the Sakai's output. This compactness came at a price. The cylinders were tightly packed, making cooling difficult. The tight design required precision manufacturing that tested the limits of Japan's industrial capability. When everything was machined correctly, when the materials were of high quality, when skilled workers assembled it with care, the Homare performed brilliantly. Japanese test pilots praised its power and smoothness, but mass production revealed the truth. Japan's manufacturing infrastructure couldn't maintain the tolerances the Homare demanded. Cylinder heads, which required dozens of thin steel plates to be removed from hot molds within strict time limits, were manufactured by workers with insufficient training. By 1945, many of these workers were high school students, drafted into factory service, doing their best but lacking the skills required. Quality control became a nightmare. Some Homares left the factory producing close to their rated power. Others struggled to reach 1,300 horsepower, far below design specifications. Field mechanics reported chronic problems. Engines overheated in tropical climates. Fuel systems malfunctioned during negative G maneuvers, cutting power at critical moments. Cylinder heads cracked, bearings failed. The metallurgy simply wasn't up to the stresses involved. Japan had good engineers but lacked the advanced alloys and heat treatment processes that American manufacturers had spent decades perfecting. The material shortages made everything worse. By 1943, Japan was running out of everything. High-quality steel became scarce. Aluminum supplies dwindled. Specialized alloys for bearings and valves were unavailable. Engineers were forced to substitute inferior materials, hoping they would hold up long enough. They rarely did. A Nakajima Ki-84 Frank fighter, powered by a Homer engine, had a design, top speed of 388 miles per hour. American forces captured one intact late in the war and tested it. With proper fuel, proper maintenance, and American quality standards, they achieved 427 miles per hour. The same aircraft, 40 miles per hour faster, simply because it was maintained correctly and fueled properly. This revealed a devastating truth. Japanese designs weren't the problem. Japanese pilots weren't the problem. It was the system. The factories, the supply chains, the training, the quality control, all had broken under the pressure of total war. Meanwhile, American factories were producing miracles. Pratt and Whitney's manufacturing system was a marvel of industrial organization. The company didn't just design engines, they designed the tools to make engines. They designed the training programs to teach workers. They designed quality control systems that caught defects before they became failures. Each R-2800 was built from components manufactured to identical specifications. A piston made in Hartford was interchangeable with one made at Ford's River Rouge plant in Detroit. A crankshaft forged in Pennsylvania fit perfectly into a crankcase from Buick. This interchangeability meant that repairs could be made anywhere, using parts from any source. Japanese engines lacked this standardization. Each manufacturer had slightly different processes. Components from one factory might not fit properly with those from another. Field repairs required specialists who could file, adjust, and adapt parts to make them work. In the heat of battle, with limited tools and constant air raids, this was often impossible. The American system also emphasized maintainability. Engineers designed the R-2800, knowing that mechanics in forward areas would need to service it quickly, often under combat conditions. Panels opened with quick-release fasteners. Major components could be swapped in hours. Spark plugs were accessible. Oil filters could be changed without special tools. Japanese engines, beautiful in their engineering, were often nightmares to maintain. Accessing certain components required partially disassembling the aircraft. Some maintenance tasks required specialized tools that existed only at major depots. And as American bombing destroyed those depots, Japanese forces found themselves with aircraft they couldn't repair. The production numbers told a story of industrial dominance that couldn't be overcome by any amount of tactical brilliance. By the end of World War II, America had produced over 300,000 aircraft. Japan produced approximately 76,000. But raw numbers didn't capture the full disparity. American aircraft were generally larger, more complex, and better equipped. They carried radar, advanced radios, extensive armor protection, and redundant systems. Japanese aircraft prioritized lightweight and maneuverability, sacrificing protection and equipment to maximize performance. This reflected not just different design philosophies, but different industrial capabilities. America could afford the weight. They had engines powerful enough to carry it. Japan couldn't. Their engines, even the best ones, struggled to match American power output. The Corsair weighed over 14,000 pounds fully loaded. The Zero weighed less than 6,000. The Corsair could carry 2,000 pounds of bombs. The Zero carried nothing externally in its original configuration. The Corsair had armor plate protecting the pilot and self-sealing fuel tanks that prevented fires. The Zero had neither for most of the war, trading protection for range and agility. These weren't arbitrary choices. They reflected what each nation's industry could produce. America built engines that could lift heavy aircraft with heavy weapons and heavy protection. Japan built engines that required light airframes to be competitive. And as the war progressed, even those light airframes became difficult to produce. The supplier network that supported Japanese aircraft production was fragile. Unlike American manufacturers who consolidated production in large, protected factories, Japan relied on hundreds of small workshops and family businesses. These suppliers produced specific components, bolts, brackets, small parts, that were then delivered to main assembly plants. It was an efficient system in peacetime but catastrophic under bombardment. When American B-29 seconds began systematic firebombing of Japanese cities in late 1944, they destroyed not just the main factories but the entire ecosystem of suppliers. A factory building could be rebuilt, but a skilled machinist who died in a firebombing could not be replaced. His knowledge, his craftsmanship, his ability to produce components to specification died with him. By early 1945, Japanese aircraft production was collapsing not from lack of factories, but from lack of parts. Assembly. Plants had airframe sections sitting idle, waiting for engine components that never arrived, waiting for landing gear, struts that couldn't be manufactured, waiting for instruments that no longer existed. By 1944, the disparity was crushing. America was producing thousands of Corsairs, each with an R-2000-800 that worked perfectly. Japan was struggling to build hundreds of fighters with engines that worked sometimes. The mathematics of attrition were brutal and inevitable. The Corsair itself was a machine of contradictions, difficult to fly, yet extraordinarily effective. The long nose that gave pilots such poor forward visibility was necessary to house the massive R-2800. The inverted gull wings that made it so distinctive weren't aesthetic choices but engineering solutions. The wings met the fuselage at an angle that minimized drag while keeping the landing gear struts short enough to retract into the wings. This reduced weight and complexity. The propeller was a monster, 13 feet 4 inches in diameter, the largest ever fitted to a fighter aircraft at the time. It was necessary to absorb the R-2800's power, but it created ground clearance problems. Hence the gull wings, lifting the propeller higher without requiring impossibly long landing gear. Everything about the Corsair was a compromise between the needs of the engine and the limitations of airframe design. But the compromises worked. On February 12, 1943, Marine Fighting Squadron VMF-124 took their new Corsairs into combat for the first time over Guadalcanal. The pilots were nervous. The Corsair was tricky, unforgiving of mistakes. But once airborne, with the R-2800 roaring and 1,800 pounds of thrust pushing them forward, doubts vanished. They engaged approximately 50 Japanese Zeros that day. The Zeros were legendary for maneuverability, flown by experienced pilots who had fought since the war's beginning. But the Corsairs were faster, could climb higher, and could dive away from any engagement. In a turning fight, the Zero had advantages, but Corsair pilots didn't turn with Zeros. They used altitude, speed, and the R-2800's power to dictate terms of combat. Dive in, shoot, climb away. The Zero couldn't follow. Lieutenant Kenneth Walsh, one of VMF-124's pilots, described it simply: the F4U could outperform the Zero in every aspect except slow-speed maneuverability and slow-speed rate of climb. It took time, but eventually we developed tactics that overcame any shortcomings. Those tactics, combined with the raw power of the R-2800, created the 11-to-1 kill ratio. The Corsair's 650 caliber Browning machine guns delivered devastating firepower. Each gun carried 390 rounds, enough for sustained combat. When all 6 fired simultaneously, they produced a stream of armor-piercing and incendiary rounds that could tear apart enemy aircraft in seconds. Japanese pilots reported that Corsairs seemed to appear, from nowhere, screaming down from altitude with that distinctive whistle, guns blazing, then climbing back to safety before defensive maneuvers could be completed. The psychological impact was enormous. By mid-1944, Japanese aviators recognized the bent wing silhouette instantly and treated Corsair encounters with extreme caution. Some refused to engage at all, breaking off when they spotted the inverted gull wings. The most famous Corsair unit was Marine Fighting Squadron VMF-214, the Black Sheep Squadron, commanded by Major Gregory Boyington. Between August 1943 and January 1944, they shot down or destroyed over 200 Japanese aircraft in just 84 days of combat. Major Boyington himself was credited with 22 victories flying the Corsair, bringing his total to 28, including his earlier service with the Flying Tigers in China. He was shot down over Rabaul on January 3, 1944, and spent the rest of the war as a prisoner. After his release, he received the Medal of Honor. His success, and that of his squadron, demonstrated what American pilots could achieve with proper training, sound tactics, and the immense power of the R-2000-800 behind them. Over 64,000 sorties flown, over 2,000 Japanese aircraft destroyed, only 189 Corsairs lost to enemy action, the lowest loss rate of any American fighter in the Pacific. The R-2000-800 rarely failed in combat. Pilots came back with cylinders shot out, oil streaming, parts of the cowling blown away. The engine kept running. There are documented cases of Corsairs returning to base with entire cylinder heads missing, flying on 17 cylinders instead of 18. Pilots unaware anything was wrong until ground crews pointed out the damage. This durability came from the 4 years Pratt and Whitney had spent perfecting the crankshaft, from the obsessive attention to cooling, from the quality of materials and precision of manufacturing. Every decision, every test, every failure analyzed and corrected, had built an engine that could survive conditions its designers never imagined. Japanese pilots who faced Corsairs late in the war were often poorly trained, flying aircraft with unreliable engines, short on fuel and ammunition. But even earlier, when Japanese pilots were among the best in the world, the Corsair held advantages they couldn't overcome. Speed and power, delivered by an engine that represented the full might of American industry. Captain Tanaka's report wasn't just about the R-2000-800's technical specifications, it was about the system that created it. The specialized steel mills that forged crankshafts to microscopic tolerances, the machine tool manufacturers who built the equipment that built the engines, the quality control inspectors who rejected any part that deviated from specifications, the training programs that turned civilian workers into precision machinists in months, the supply chains that ensured raw materials flowed without interruption. Japan had none of this at the required scale. They had some steel mills, but not enough. They had machine tools, but many were outdated. They had skilled workers, but not millions of them. They had supply chains, but American submarines and bombers were destroying them. The gap between the two industrial systems was wider than the Pacific Ocean. It was a gap that couldn't be crossed by courage, by technical innovation, or by divine wind. It could only be crossed by building the infrastructure to support mass production at American scale, and that would take decades. Decades Japan didn't have. By the time the Corsair arrived at Yokosuka, the war was already over. The Japanese engineers who dissected it were examining the corpse of their own empire, understanding too late why it had died. The R-2000-800 they found inside wasn't just an engine, it was a message from a different world. A world where factories could produce precision machinery by the thousands, where workers could build identical components day after day, where the system itself was the weapon. In the final months of the war, Japan attempted desperate measures. Kamikaze attacks, human-guided missiles, plans for an invasion defense that would sacrifice millions, but none of it could change the fundamental equation. America could build faster than Japan could destroy. For every ship sunk, 3 more launched. For every plane shot down, 10 more took off. The R-2800 engine, in all its mechanical perfection, was the embodiment of this unstoppable production. Reliable, powerful, present in every theater of war, it represented not just American engineering but American industrial supremacy. When the engineers at Yokosuka finally reassembled the Corsair's engine, fitting each component back into place, they ran it. The Japanese had no suitable fuel, no proper testing equipment, no reason to do so except to hear it run. The R-2800 started on the first attempt. It idled smoothly, oil pressure steady, temperatures normal, 18 cylinders firing in perfect sequence, just as they had in Hartford, Connecticut, years before. It sounded, witnesses reported, like thunder captured in steel. After 5 minutes, they shut it down. There was no point in wasting what little fuel remained. Sato Kenji stood beside it in silence, hand resting on the cowling, feeling residual heat radiate through the metal. "We could build something like this," he said quietly to Tanaka. "In 10 years, maybe 15, with the right investment, the right training, the right infrastructure. We could do it." Tanaka nodded. "But we needed it 5 years ago." That was the tragedy. Not that Japan lacked capable engineers or innovative designs, not that their pilots lacked courage or their factories lacked potential. The tragedy was timing. The war began before Japan's industry was ready for it, and America's industry had been ready since the beginning. The lessons learned from the captured Corsair would shape Japanese thinking for decades. When Japan's aircraft industry was reborn in the 1950s, after the American occupation ended, engineers remembered the R-2800. They remembered the importance of manufacturing precision, of standardization, of quality control systems that ensured every part met specifications. The companies that rose from Nakajima's ashes, Fuji Heavy Industries and Prince Motor Company, applied these lessons to automobiles. Subaru cars, descendants of Japanese wartime aircraft manufacturers, would become known for reliability and precision engineering. Toyota, which had attempted to copy American Jeeps during the war with limited success, studied American manufacturing methods obsessively. They sent engineers to American factories, learning not just how to design products, but how to build production systems that ensured consistent quality. By the 1970s and 80s, Japan had mastered mass production manufacturing in ways that sometimes exceeded American capabilities. But that transformation took 30 years of dedicated effort, investment, and learning from defeat. The Corsair itself continued flying long after World War II ended. It served with distinction in the Korean War, where it primarily performed ground attack missions. Late-model F4U Corsair and AU-1 variants carried heavy bomb loads and rockets, supporting United Nations forces with devastating close air support. The R-2800 engines, by then evolved to produce up to 2,500 horsepower in some variants, proved as reliable in Korea as they had been over the Pacific. The last combat use of the Corsair occurred in 1969, when air forces in Central America flew them in regional conflicts, a testament to the design's longevity. Some Corsairs remain airworthy today, treasured by collectors and displayed at air shows where the distinctive howl of the R-2800 still draws crowds. These flying museums represent more than just aviation history. They represent the moment when industrial capacity became as important as tactical brilliance, when the ability to manufacture excellence at scale determined the outcome of global conflict. For Captain Tanaka Yoshio, the war's end brought both relief and profound sadness. His detailed technical reports on the R-2800 were filed away, read by American occupation authorities, and eventually archived. They represented some of the finest technical analysis conducted by any nation during the war, thorough and honest assessments unclouded by propaganda or wishful thinking. After the war, Tanaka worked briefly as a consultant for American engineers studying Japanese aviation technology. He answered their questions patiently, explaining Japanese design philosophies, manufacturing constraints, and the challenges they had faced. In 1953, he visited the United States for the first time, touring Pratt and Whitney's facilities in Connecticut at the company's invitation. He watched R-2800 engines being assembled, saw the quality control processes, met the engineers who had designed the systems he had studied so carefully 8 years earlier. At the end of the tour, the plant manager presented him with a small component, a cylinder head from an R-2800, polished and mounted as a display piece. "You understood our engine better than most of the people who built it," the manager said. "You should have one." Tanaka kept that cylinder head on his desk for the rest of his life, a reminder of what he had learned, what Japan had lost, and what it would take to rebuild. The story of the captured Corsair is ultimately a story about systems, not individual genius, not isolated innovations, but the complex interaction of design, manufacturing, quality control, supply chains, training, and logistics that transforms ideas into reality. Japan had the ideas. They had brilliant engineers who understood aerodynamics, thermodynamics, and mechanical engineering as well as anyone in the world. What they lacked was the system to turn those ideas into thousands of reliable engines, produced consistently, maintained easily, and delivered wherever needed. America had built that system over decades, investing in machine tools, training workers, developing supply chains, and creating manufacturing processes that prioritized reproducibility over artisan craftsmanship. The R2800 was the culmination of this approach. Not the work of a single genius designer, but the product of hundreds of engineers, thousands of workers, and an industrial infrastructure that had been decades in the making. When Japanese engineers disassembled the Corsair's engine and found perfection in every component, they weren't just examining American technology, they were examining American civilization, its values, its priorities, and its capacity to organize human effort toward a single goal. That examination led to an uncomfortable conclusion. The war had been lost not on December 7th, 1941, when Japanese aircraft struck Pearl Harbor, but years earlier, when industrial capacity became the determining factor in modern warfare and Japan had not prepared for that reality. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.